So I will start. Yeah, thanks for the introduction. So this is Michael. So I was thinking about what to give at such a workshop, Pointcloud workshop series. And so in the end, yeah, I give this title of Deep Learning for Semantic Segmentation of 2D and 3D data. So I wouldn't only talk about the Pointcloud data, but also about images at the beginning. And so I'm Michael from ITC. And so what is my main, let's say, research field? So my group has been working on so-called visual scene understanding. For example, here we have different, let's say, scenes. For example, the first one, like from terrestrial imagery, and then from the UV perspective or from the aerial images we are interested in, and then later for the point cloud, so 3D point cloud. So the task would be like object detection and semantic segmentation, 3D reconstruction, and scene abstraction. Well, maybe at the beginning, I will give you a few slides that what my group's been working on in the last couple of years, just to give you an impression that what is this like a visual scene understanding about. Well, it's not all of them, but then we are working on part of that. So one example is that so my former PhD student, Jen Chao, is working on the landscape modeling and updating. So this basically is on the change detection and classification. So the method we used is the SAMIS and convolutional neural network. So here example that I put it here. For example, on the top row is the airborne laser scanning point cloud, airborne laser scanning point cloud captured, and then on the lower row is the point cloud generated from the photograph. Yeah, so airborne photogrammetry that using the photogrammetric process that we get in the point cloud. And we can also get in also photos, for example, and then we put into the network to do the change detection. Well, here this is quite simple. We only detect the changes in the buildings. Yeah, so for the building height, the change lowered or the higher or lower or stays the same. So that was the project about. So I would like to talk another one and jump to another one, which is funded by EU, Sophie. So working on the visual boundary mapping. So the project is about using the very high resolution UV data for very rapid mapping of the parcel boundaries. For example, here's the example that I gave here. So let's say this is a high resolution UV imagery, and we want to, let's say, mapping the boundaries, so where the fence, where the house, and with trees and the bushes, for example. And this is for, let's say, most of the Eastern African countries, including Ethiopia and Kenya. Well, we actually, at the beginning, we used the random forest, very traditional method, and later we gradually actually using also the convolutional neural network for that purpose. Another project here has been working on the semantic segmentation from the UV data. So here you see an example. So this is manually labeled, let's say, from the UV data. So manual labeling such image would take 2.5 hours because it's quite detailed with some categories. For example, the trees and the road and the vehicles and the buildings. So the method he used in the project is using CNN. And then if we're talking about, let's say, sequential UAV data, the image sequences, and then he also using the so-called recurrent neural network. So later I will talk about this project in more detail. And another one, Yaping. So she just finished last month on the this month, sorry, on the semantic segmentation of large-scale point cloud data. So it's mainly on the airborne laser scanning data. So she used the CNN for that purpose, and then later she also using the so-called weakly supervised learning method. And so I will also talk about this in more detail in the later of the talk. So yes. yeah, wait for a minute, and we'll talk about that. And another one that the project from Florian, and so that's a bit more, let's say, non-photogrammetry. It's more computer vision. So he's working on the so-called geometric deep learning. So, for example, like 3D shape fitting. Yeah, so giving here for giving an input image, so the single image, indoor image, and then he wants to infer the 3D. So directly infer 3D is actually quite difficult. So what he did is that to represent the this 3D this thing, yeah, of giving the image only image input and recover the cuboid. Yeah, so basically using the cuboid to represent the object in the scene, for example, the walls, the floors, and the bed and desk, for example. Yeah, so he uses CNN and self-supervised learning. And another project just finished last year, Wintong, is working on the scene graph generation. And so the scene graph generation is mainly talking about the, let's say, the relationship between the objects. Yeah, so it's called scene graph. And so here is example. For example, on the left, you have this natural scene. Yeah, so you see there's a train, yeah, and the buildings and trees, for example. And then on the train, there's windows and doors. And so this kind of most likely the object detection you are familiar with. While on the right side, so it's not only detection. For example, here you see the, let's say, train has window, right? Train has window GT1 and window GT2, window GT3. So it's kind of relationship. So it's also the kind of spatial relationship. For example, the building one is behind the tree one. I think I can also use in the pen laser point. Yeah, so maybe you can see here. So here the window one and has the train has this window, right? And then also the building one is behind the tree one. So it's kind of also spatial relationship. So it's not only spatial relationship, but also semantic relationship. So it has or have other verbs under that. So such work is on under this so-called scene graph generation. So the method using the graph convolution network, and also there is a transformer-based method. Okay, so very brief and very fast if you're interested, and we can talk about later after the talk. Okay. So now I come back to the semantic notation, the main topic of today's talk. So what is semantic notation? Well, here I'm giving an image example, but you can also think about a point cloud example. Yeah, so this has been very well known back in the ECCV 2006 by Jamie Shelton and the others from Microsoft Research at that time. So basically, they built up a large data set at that time. So basically, even giving an image, yeah. So we want to label every pixel in the image into one of the categories. So these are the 21 classes. So this is predefined. Yeah. For example, here you have the airplane. Yeah. So on the third one, airplane, and then the buildings and the road and buildings and water and the sky. So these are the classes being predefined, and we want to infer that automatically. So at that time, so actually a very popular method before everyone's now doing deep learning, but before that, the very popular method is actually so-called using conditional random field models. Maybe some of you heard of that, or some not. Well, this was very popular, like overtaken by the deep learning method. But then before that, it was like more than 10 years or 15 years on this so-called CIF models. And so the basic idea is that basically giving an image, and then we model every pixel as a node in the graph. Yeah, and then you basically can create such a graph, and then you train this so-called the energy function, so EX, and then this is the unit potential and the pairwise potentials, and these potentials can be trained, for example, using random forest, yeah, and the other methods. And then in the end, infer the let's say the final segmentation, for example, like this one. Well, this actually was the best result they can get back in 2006. Well, you see there's some errors right here. The sign is wrong, so this should be building. Grass is correct, and tree is correct, and sky is correct. So it's actually a pretty difficult task even now. So you cannot get 100% accurate with such semantic segmentation results. Well, obviously then deep learning take over back in 2012. Yeah, so this is one of the 10 breakthroughs labeled by MIT Technology Review. So now everyone knows, yeah, this deep learning. So actually, with the compared with the massive amount of the computational power, right? Well, at the beginning, so I just show you one example that this at first, like in the 90s, yeah, this very early neural network called CNN, and so this such neural network has been actually designed for classify these kind of digits, yeah. So handwritten digits, like this handwritten number 3, and then it's going to the network. So this neural network with very specialized connectivity structure, basically using convolution, and then stack multiple stages of the feature extractor. So if you're going higher, the higher the compute more global and more invariant features. In the end, there's classification layer. But this is kind of understandable because the task that time is really try to classify these digits, right? So in the end, you just need to say this is number 3 or number 4, number 5. Yeah. Well, this is actually very successful, and even before the yeah, everyone working on deep learning. So on the handwritten text or digits, it's actually very successful, and also the let's say the traffic signs. So what's surpassing the human performance on the traffic sign data set. But before the, let's say 10 years ago in 2012, it's actually less good at a bit more complex data set. So at that time, people are working on the so-called Caltech data set, 101 or 256. So this is basically the classification data set, and with few training examples. So, so it's not that well known. So some small group of people working on deep learning, not like compared to nowadays, and most people working on deep learning. So well, then in 2012, news that this AlexNet came out, right? So I just briefly review that. So it's actually very similar to the network back in the 90s. But what is different is that it's been now a very bigger model, yeah, and much larger parameters. You have 60 million parameters in there, and at that time there was way more data for training because of the ImageNet. And then we have GPUs for the implementation, and then you have this also called better regularization, yeah, for training. You have to basically drop out techniques. So basically just after this AlexNet, then okay, everyone think, okay, this is really something, and then we should look into that. And then after quite some years, and then basically this deep learning basically took off, right? But in the rest of the talk, so I will talk about a few projects that my PhD student was working on or was working on. So one project is on this UAV and semantic segmentation. So here you have this UAV imagery, and then there's manually labeled this ground truth. And as I said, it took like 2.5 hours to label and verify them. Yeah, so label, and then someone else need to verify that if it's correct or not. So you will see that it's quite detailed, but it's not everything. Yeah, you see also the black space. So this black space is the others. Yeah, so everything not belong to these different categories to this black space. So then we built a basic data set. At that time, we want to do the research, and then we couldn't find an appropriate data set and for the semantic segmentation for the UV data. So I think starting 2017 and then until 2019, so basically 2 years time, then we actually built a data set for that. So it's been captured with the DJI drone, so Phantom 3 and Phantom 4. So it's quite flexible. And then we have very high resolution. And on purpose that we actually capture data on the very complex and dynamic things near the street. So in the end, so we actually capture more data, but then we have to label them. So that's quite costly. So annotation is really costly. So in the end, we have like 42 small video sequences, yeah, in different places. So each one has around 1 minute or 50 seconds. And then every 5 seconds, we basically label, let's say, giving the ground truth labeling. So in the end, you have we got like 420 labeled images, and we split that into 200 for training and 70 for validation and 150 for testing. Okay, so this is still let's say active. So one can still do testing under this data under this website, this UAV ID.nl, and this work is being let's say published now. Is open access in the IPL journal back in 2020. And so what does look like? This data set look like? If you see that on the bottom, so you have this imagery taking of different places. You see there's a lot of street views, right? So you have a lot of vehicles or the cars, yeah, on the street. And then the second row here is the ground truth labeling, and the third row is basically to overlay to the imagery. Okay, so up this is the histogram, but then this is only the pixel number histogram. So you'll see that the most, let's say, largest category is actually buildings, right? You have basically large buildings, and then you have the vegetation, the other trees. Sorry. So here we separate trees and vegetation because trees are taller, and then basically lower vegetation, and then we have a road. But we also separate the two types of cars. So one is called a moving car on the street, and the other is the static car, let's say standing still. Because we capture the video, we actually can distinguish that from the previous frame and the next frame. So you really see the let's say if it's dynamic or it's static. And then there's also a very small amount of the humans, because of the very high resolution, one actually can see some part of the humans. Okay. And we developed this called 3 ways of labeling. So one is using the script, and you basically scribe that and then giving the label. And then secondly, it's called superpixel-wise labeling. So basically, we do unsupervised superpixel segmentation, and then you basically click that and giving the label. So another one is kind of conventional. Yeah, you're basically giving a polygon and then giving a label to that. For example, this is a building. Yeah, so these are different ways that of the labeling. So we also have the labeling tool available. So for that project, we also offer the kind of standard network models. So these are the few of the networks that we provide. We tested also, for example, the FCN, so fully convolution network, and then the dilation network, and then the UNet, so basically encoder decoder structure. Yeah. So I will not go to detail about these network structures. So if you're interested, well, we can always look at papers, and also these are quite well-known network. And then in that paper, we also extend to a fourth version of the network called the multi-scale dilation network. So basically, this is extension for the dilation network, but then we count for the multi-scale version. The reason we actually for that development is we observe that because of so here the UAVs are actually I forgot to mention that it's actually the oblique view. So it's not NIDAR view, it's oblique view. So with oblique view, we actually have a very, let's say, FOV, field of views, very large FOVs. So let's say the object, for example, the cars very closer to the camera are much larger than cars are, let's say, further away. And then it's the same thing for the buildings. So we actually want to, let's say, account for such scale difference. So that's one of the reasons why we actually developed such so-called multi-scale network. Okay, and just give you an impression of some numbers. So you can look at the last column here. And so the first block here is actually the without pre-training. Yeah, so basically we have all this network FCN and UNet, and then we're basically using our UVID data set and to train the network. So you will see that. So from FCN, so it's kind of standard semantic citation network. It's like 35.6. So this is IOU metric. So intersection over union metric. Okay, so it go up to, let's say, with MSC multi-scale dilation network, it's like 42. Yeah, so it really increased quite a lot because this is IOU. And well, with pre-training, so the second block is pre-training. So with pre-training, all of them actually increase the accuracy. So the pre-train is pre-trained on the Kitty data set. Pre-trained on the cityscape data set, because we have the cityscape data set. So this is also the standard for this load view, yeah, a semantic citation data set. And then we can come up to almost 50%. The third block is, yeah, adding the so-called feature space optimization. So basically, this is accounting for the different frames in the video. So basically, accounting the kind of the temporal information. So it's getting a bit better. So not that, let's say, in terms of the numbers, it's actually not that much, right? It's like 0.3%. But then in terms of the visual accuracy, yeah, the visual performance is actually much better because you have this kind of temporal consistency there. Okay, so we also, in that paper, we also investigate, yeah, if this kind of deep supervision, so different stage of supervision, if it works or not. Yeah, so you will see that the hypothesis that deep supervision, yeah, basically it's working. Okay, I think I can show. I hope I can show that. How can I show this? So maybe. Okay, so how can I show this? All right, I think I have to make it back. So basically, I want to show a video, but I have to make this go away.
I think maybe if you stop sharing
Yeah,
this instance.
no, it's fine.
Oh, no, here we go. Yeah, that's good.
I can get it. Yeah, great. Okay, thanks. Yeah, I don't know if you can see that actually. Yeah, it's working, but maybe it might be too fast. Yeah, just stop here, and you might see some result of this. Yeah, so this is a kind of test image. It's quite clouded, with the, let's say, vehicles and some of the people, humans, and also of the environment. Yeah, so you will see this is image, and then on the bottom there's the ground truth. Yeah, so it's manual labeled, and on the right side then we have a different network prediction result. So you might see, yeah, it's not that you might not see that clearly, but then maybe some part of the, so in general the vehicles actually being detected, well, pretty okay. Yeah, so if you see that, so this blue ones, they are the vehicles, but those pink ones is the static car. So the blue ones is the dynamic car. So actually being predicted pretty well, and also the buildings, and yeah, so most of them are actually working pretty well with the buildings, and some of the vegetation. So in general, what I want to say is that it's actually working pretty okay-ish, but not to all degree, right? So some of the classes are not that good. Yeah, maybe just show you then. You might not see that. Yeah, so just check if it's working. So for example, here, like, so if you see the ground truth, these buildings are labeled, yeah, pretty accurate in actually. Well, so none of these, let's say, the network actually predict, let's say, perfectly on the building boundaries. Yeah, so this is one thing that we may need to work on further. So I will not show further on this. So so there's one extension for this work, because previously that what we have been doing, so this UAVnet is all fine. Yeah, so UAV on UAVID, but the problem is that there it's actually taking quite long for the inference time. So if we want to later to, let's say, to deploy that to on the onboard, for example, onboard drone, onboard UAVs, or the other onboard system, so it will be just too slow. Yeah, and so later then we have a project on so-called, we want to make it pushing basically for the accuracy, not only for the accuracy but also, let's say, for the speed. So this is the work we have been done last year for the ICRA, so the robotic conference, back in 2021. It's called real-time semantic citation. So on the right side, you will see that these are the cityscape images, and then this is the result, the prediction result. So you will see that so those are the cars and the road, and then the pedestrians and some of the sky. Yeah, so more or less it's actually fine. So the mean IOU score for the cityscape that we actually can get into almost 76%. While this is not the top, yeah. So at the moment, so some measures can go into, let's say, 83 to 85% of the IOU score on the cityscape. While we have this 76% on this data set, but we'll maintain the 76 frames per second. So that's actually pretty fast on a modern GPU at NVIDIA, 2080 Ti. While on the, let's say, very efficient GPU, so this is Jetson NX. So for this one, so it's much smaller, and you're getting like 8 frames per second. So it's still not up to, I think if you really want to make it, to deployment and in the deployment and for real time, you might get up to 15 frames per second or 20 frames per second. So there's still some space to push. So the main idea is that, so I'll just show you one slide for the main idea. So not go into that detail again. So let's say given the image, we actually have two branches. So one is called contextual branch and the other called spatial branch. So the contextual branch is basically, you can think about it's kind of context aggregation information from the context. So here using so-called mobile net. So that's actually a very small network. So we make it even smaller. So mobile net v3 small version. And then we have this different attention models. And then for the spatial branch, so this standard, basically you have convolution network and then spatial normalization and then rectifier union. And then you have this convolution. And then in the end, we do the model fusion, with two branches we're fusing together. So basically the idea is that for each block, this modules, we want to squeeze the model parameters. So I just show you the result for the cityscape validation set. So you might see that, so this is the image. On the last column is the ground truth. Yeah, so it's manually labeled ground truth. And then these are two comparison methods. So this one, the second column is the SwiftNet, and the third column is our network result. Yeah, so you might just see that, for example, on the third row. Yeah, so this is basically a vehicle. yeah, and this is different type, yeah, kind of bus. And then you see that here it's actually quite difficult to distinguish, because they are quite close together. And then with the contextual information, and one can actually recover such kind of boundaries pretty nicely. Yeah. Okay. Okay. Yeah. So this is some numbers. So maybe what's important is the so not only the IOU number. So this is basically representing accuracy, but also the for example, the memory consumption, and then how many flops, and how many parameters, and and also the let's say the frame per second. Well, you might see that so ours is not the best compared to the frame per second, because there's a fast as CNN getting to, let's say, more than 100 frame per second. But then the accuracy is actually pretty low. So if we check the result, it's not that good. It's 68%. Yeah, it's not as good as the others. Okay, so I think nowadays, I mean, it's published last year, but I think nowadays it's even better network. So there's some other better network built on this. So by set network. So some network built on top of that, and actually they're giving you better, even better. I think it's similar accuracy, but much faster, maybe up to 100. So the field is still going on. So maybe I show you this. I think this might be interesting. I just so here. So we also test actually on the UAV data set. So this is another UAV data set. So this is another UAV data set. Yeah, so a bit simpler. So this imagery, and then with other competing method, and then with our method. Okay, and so maybe I think this is what I want to show you. So this is the real-time performance on the cityscape data set. So it is on the full resolution imagery. So 2000 by 1000, and then it has the test accuracy of almost 76%. And as I said in past, so you have the 76 frame per second on the the modern GPU, and then 8 frame per second on this very small GPU, the adjacent GPU. So the adjacent GPU can be put on the basically on the UAVs. Okay, so maybe I can show you this. Yeah. Okay, so you'll see that all these vehicles and the road actually segmented pretty correctly, but you also see that there's actually the jittering effect, right? So it's like flipping back, because this is not done sequentially, so it's only done per frame. Yeah. So this is for the UAV data set, and you also see this flickering, jittering effect. But actually per frame, it's actually doing pretty well. Yeah, with all the buildings and the road and the vehicles being segmented. Yeah, pretty good. Yeah, so we were not able to make it, let's say, as smooth as possible, because we cannot using the we did not using the, let's say, the neighboring frame information, because if we're using that, it will take a much longer time to process, so we cannot have the real-time performance anymore. Okay. Okay, so this is so far for the 2D image semantic notation. So I'm going to use in the rest of time talking about more on the 3D point cloud. So this, you might, let's say, more familiar with this part. But I would like to focus on the, let's say, airborne laser scanning point cloud. So this is another, let's say, PhD project done by my student Yaping. Yeah, so I think all of you know the airborne laser scanning. Yeah, we also do that, and some of you also do that. Yeah, so it's an important data source. Yeah, for 3D modeling. For example, here you have the some examples. So the interpretation of this essential step for the downstream products, right? So we're talking about the semantic labeling, yeah, for the 3D point cloud. And so here there's a data set called the ISPRS 3D and data set. So you have two parts, section A and section B. And so on the left side, so this is basically a training set. Yeah, so we have the these classes, yeah, with power lines and lower vegetation and cars and facades and roof, for example, and trees. So it also distinguishes trees and a shrub. So everything lower, I think lower than 2 meters is shrub, and then taller is trees. So on the right side is the test data set. So this section B. And so this is the new network we developed last year. That is called the local and global encoder network. So this is actually specific for the airborne laser scanning point cloud. So the input here is the let's say the point cloud, 3D point cloud, but also the segment. So actually, we also were using the kind of unsupervised segmentation. For example, one can use the mean shift or the other clustering method to do the unsupervised segmentation, and then we put it into the network. So we build this network, and so this is called hybrid 2D and 3D block. I think I will explain that in the next slide. And then this is basically, so if you see the structures, basically this kind of encoder decoder structures, right? And then in the end, we have the here the so-called spatial channel attention. So basically, we're putting some attention models on top, and then we have the classification results. Okay. So to show you, so what is this hybrid, this 2D and 3D and convolution block? So here, so the top row is the conventional one. Yeah. So inside this is called 3D KP-conv, and so what we did in that paper, or Yaping did in that paper, is that she actually extend that from the 3D and KP-conv and then to both 3D and 2D, and this shows to be appear to be actually quite attractive. So I will show you an example here. So for example, this is the point cloud data. So on this area, yeah. So the top one here, on the right side, the top one here is the 3D kernel point. Yeah. So if you want to apply the 3D KP-conv, then that's the kernel points one would apply. While the 2D kernel points, so these kernel points are shown in orange. Yeah. On the right side on the bottom. So the hypothesis here is that actually for the airborne laser scan data, you might see that there's a lot of these planar structures, right? So only the 3D. So this bit, so for the, let's say the point cloud data, so it might be counterintuitive because you might think, okay, the 3D curve, yeah, 3D convolution is actually enough for that. But then we found out that actually explicitly that modeling this 2D part, 2D KP-conv actually is quite beneficial because you have a lot of these planar structures, yeah, like ground, for example. So that's the reason that we introduce this also the 2D kernel in there. And then there's the in the last before the classification layer, we have the spatial channel attention. So this channel attention obviously is kind of inspired by the recent all these attention models. So it's basically giving you one that kind of attention model to some specific classes. Yeah. I think due to time, I will also kind of skip that. I'll show you some results instead. So that's actually kind of result one can get from this network. And so this is a test result. So you might see that from this kind of block that you might see that these results. Yeah. So so these are the labels. So red are the roof. Yeah. So the roof part is actually most is actually pretty correct. And then there's also some vegetation and trees and shrubs and the road. Here, this is better. So you might just see that. So overall, right, the red part is basically the wrong prediction part, and then this gray part is correct ones. So overall, it's actually pretty good. Here you see, well, there's still quite some wrong predictions, but the overall impression actually is pretty fine. And I'll show you here is the effect of this kind of channel attention model. So I want to advocate that maybe such kind of attention model is quite useful. So we also see the recent work that some others, the other authors, they're actually using different type of attention model, like transformers and the others. They're actually giving better numbers in terms of the accuracy. Yeah. So you'll see that let's say with channel attention, for example, especially for some kind of power lines, yeah, these kind of very long, elongated structures, and such kind of attention model actually giving you better results, for example, compared to basically if you look at the first row, yeah. So here you can actually recover some kind of points on the power line, compared to the ground truth on the right side. So this power line is actually quite difficult because it's very long and very sparse points. So I'll show you the numbers here. For example, the power line is on the first column. So now we can get up to 76% of the accuracy, which is actually pretty good and compared to the previous ones. So overall, yeah, I think on average that the average F1 score, we're kind of the best at the time, while the overall accuracy is a bit worse than the previous one. But I noticed that this year they actually been a few papers, they're pushing these numbers much further, like to the 80% of the average F1 score. So there's still people working on that. Okay, so this is some result. On another data set called the DFC, and so data fusion context 2019 data set. So here what I show you is that, so they have different classes. Yeah, so you have this high vegetation and then buildings and water and bridge deck. So the bridge deck and also the ground. And so the last row is the ground truth. Yeah, so you'll see that this is ground truth, and there's also a bit of black areas unlabeled. So we don't have that in all of these prediction models. Okay, so you might see that I highlight these circle areas. So with different components, it's actually these kind of getting better and better. So the first row is the baseline, basically using the state-of-art KP-conf network, and then it's basically getting better. Yeah, it's refined and refined, and same on these other emphasis circles. For example, here, yeah, this kind of water area, and okay. Okay, I also have some numbers here. Okay, so yeah, so if you see that, yeah, just look at the last two column. So the average F1 score and overall accuracy. So adding the component give you a bit like 1% and each increasement. And then on the overall accuracy. So on the overall accuracy is actually pretty similar. So I think the average F1 score is actually more, let's say, valuable, yeah, metric one could look at. All right. So far for this one. So I want to talk about in the last couple of 10 or 15 minutes about the one of the recent work we have done called the weak supervision. Yeah, so you'll see that from previous the papers and projects we were talking about. So we actually designed the new network, and then so all of these network actually requires, I mean, you know that all the deep learning network require large amount of trained data, right? So that's actually very costly. So the motivation for this work is to reduce the labor cost, yeah, in data annotation. Okay, so what type of there's different type of weak supervision basically, and research on in the literature. So this is one of them. Yeah. So basically we have on the left is a full supervision, and then if you want to do less, one can do is basically points, right? So in the Pointcloud, you basically label points. You can label points. So it's limited point annotation. Well, it's not only so this is kind of one very standard. Yeah, you will see that in the literature. For example, this is one example from Xu and Li back in 2020 in CVPR. And so there's actually way more type of weak supervisions available. For example, so I list a few of them. So for example, bounding boxes. Yeah. So in the Pointcloud, you can actually do 3D bounding boxes. Or in image, one can do 2D bounding boxes. So the bounding box is actually much easier, yeah, compared to labeling the per point or per pixel. Well, the other one is called scribe. You basically do the scribe. And then third one is the image level labeling. So this is for the images. And then for the point cloud, you can also think about the thing level labeling. Yeah. So let's say giving a bunch of point clouds, and then you basically putting the labels for that. I think I will talk about it in the next few slides. And with limited point annotation, there's also other type of let's say indirect annotation. And so give you example about the image level labeling. So this is one of the, let's say, very common method in the literature called class activation map. So it's called a CAM. And so this example, let's giving the an image, some backbone network, and then you're basically getting the idea is basically that we say this is a bird, yeah. So you don't give a pixel level, basically a pixel level annotation, because that's very costly. While giving the image level annotation, for example, this is a bird, but then we want to kind of localize where this bird, right? So then you have this heat map here, and down there you have heat map for this kind of bird, and then do generating this pseudo labels. Say, okay, so where this bird area, right? So that's the main idea, yeah. So then the segmentation network trained with this this class activation map. Then in the end, it's kind of pseudo labels, yeah. You're generating such kind of pseudo labels and then putting the network for training. So later you will see that our method is actually a bit similar compared to the image level. So this is what we said before. So a point level, yes. So point actually is quite good supervision. Well, it's still a bit costly because you need to label every point here, right? Maybe 10% of points, yeah, compared to 100% of points. And so back in 2020, so there's another one. So this is also for the indoor point cloud. So this is indirect annotation. So our work is built on top of that. So I want to talk about that. So basically, they do not label per point, or they do not label, let's say, the whole area. What they label is that, so they're giving this part as a whole label. So for example, this let's say ground and the furniture, and so these kind of thing label, yeah, they give that to this subcloud. So they call it subcloud. So then it goes to this kpconf, yeah, standard let's say network, and then they have this different type of attention models, yeah, spatial attention, channel attention, pointwise attention model, and in the end, so now going down there to this subcloud label. So they have this so-called subcloud labels, and then back from the subcloud label, they have this so-called multi-label classification loss, and then going back to the network. So this basically going back, yeah. So this okay. So I think now I need to laser points. So this part here will go back to the network to train the models, yeah. So while the so this subcloud label is given, yeah, as training signal, while this dotted line, this element-wise maximum and the nearest upsampling. So these are not, this only forward. Yeah, so this only forward pass. Then you're getting the pseudo labels. Once the network's trained, and then you're basically getting the pseudo labels. Okay, so you're getting something like here. So that was the idea, like inspired us, let's say for our work. So this is the work that we published some months ago in ISPRS journal of Photogrammetry remote sensing. So the main idea, so well, this is looking a bit complex, but then we have like two blocks. I want to explain that a bit. So first block is let's say generating the pseudo labels. Yeah. So think about that. We're giving a subcloud. So this subcloud, let's say, giving the labels. So the power line, lower vegetation, surface, imperative surface, car, yeah, fence, roof, facade, shrub, trees, right? So we're giving that to this subcloud, and then we train a kind of an encoder. So the kpconf, for example, yeah, and then we have the let's say global average polling, and then do the multi-label classification. So because here we know that, right? We know what is inside this point cloud. So we do this multi-label classification loss. So this is the same as previous yeah, CVPR paper. And then for the inference, yeah, we do the inference and we do the nearest upsampling, and then we get in point cloud, point-wise pseudo labels. So this is actually only for train data. Yeah, so once we get these, and then we can put that back into the network, right? So now we have this, we have train data. We can put back into network, yeah, to also encoder decoder network. And then we can get in the point-wise prediction. So once we train this network, now we can do a prediction, yeah, on the test data. So the second one is called a segmentation network, and for training and for testing. Okay, so I'll show you what is the base network to generate the pseudo labels. And yeah, so here, so this actually is same as the previous one, as this network here from CPR 2020. Well, so the input, one can think about the weak labels, yeah, can be written as, so what is one here is a vector, 1 0 0 1 1 0. So what is one is that it appears in the yeah, let's say we can basically label that very fast, right? For example, here if you have let's say in ground, yeah, and the facade and the vegetation. So we have these three category as one and the other as 0. Okay, so this can be labeled very efficiently, even compared to the point labels. And so in that paper, we actually also introduce a bit new kind of loss function and to constrain the. So this is actually very weak constraint, right? You think about that. So this kind of subcloud with this weak label is actually very weak constraint. And then we can further constrain that about on the overlap. So if these two subclouds is overlapping, so then we know, for example, here on the left is, let's say, the low vegetation, car, and improved service, right? On the right side, you have all these categories. And then on the overlap, we actually know that, so this kind of automatically inferred that on the overlap, we actually have the lower vegetation and yeah, the improved surface. Well, we not only we know that, we also know that it only has these two categories, right? So that's actually quite yeah, powerful discriminative information. And well, one can do that, kind of push this idea first, so that you can actually overlapping multiple subclouds, right? On the right side, you're basically having, so with different color representing different subcloud here. So the difference, one difference that compared to the previous CPR paper is that they only have one subcloud, and then we push that to multiple subcloud with overlapping. So with overlapping areas, actually, it's way more discriminative. and we put that discriminative information as a loss function for the training. So I'll not talk too much about that. So and I show you some results here again with this ISPRS 3D data set. So it has 700 more than 750,000 points. Okay, so I'll show you one numbers, and that we're using, let's say 1% of these points. Sorry, like 7,000 more than 7,000 weak labels. Yeah, and then if 0.5% is half of the weak labels. So what we can get here is that this is on the test data set. So see that using KP-conf, what we can get is that 70% of the F1 score. So this is under full supervision with, let's say, training from the with all the points labeled. Well, if we're using weak labels, with the baseline, so this CPR 2020 paper with 1% of the weak labels, you can get to with some tricks that one can get to almost 57% accuracy of the F1 score. While with our method, we push on the overlap, and then we can get to 63%. This is only with 0.5% of the weak labels. Well, if you're using 1% of the weak labels, it pushes a bit further to almost 66% of the F1 score. So now I'll show you the result about this 0.5% of the weak labels. This is the arrow map. So if you compare to the previous, so I showed you another arrow map, right? So actually this red area is larger. Well, we're only using, let's say, 0.5% of the weak labels. Okay. So I may show you maybe another example about so there's another data set we use in the paper. It's about using AHN data. So it's on the Rotterdam. So this bigger area is using for training, and then the smaller top right area is for testing. Yeah. So then we using even less weak labels. Yeah. So we have 0.02% or 0.01% of the weak labels, and this is what we can get. So here with the full supervision, it's actually much better because it has less classes. Yeah, you see, one only has, let's say, 6 classes for this data set. So we can actually getting up to almost 92% of the F1 score. So it's actually very high with the full supervision. But with weak supervision, with baseline, we can get almost 70%, while with our method, we actually push up to 87%. So it's quite some gain there. And maybe just show you a result. This is for training data, the pseudo labels on the train data. So this is actually better compared to the test data. So on the top ones are the ground truths. So the different we enable different losses or different modules, and then you might see that if you look at the last row, so this is one of the last 2 rows is one of the best ones that one can see. So if you look at the last column of these bridges, so it's actually working pretty well. Well, it's not perfect, but then it's working pretty okay. Well, this is for the test data. Yeah, for test data, it's actually a bit worse. Yeah, if you look at the first column, so the first row is the ground truth. Yeah, so on the first column, so then you will really see that it's actually a bit worse of that. Okay, so there's another one. So this is another data set. Then we test it, and the conclusion is actually very similar. So this is a more difficult one, right? So with full supervision, then we're getting almost 80% F1 score, And with weak supervision of baseline, we got 50%. And then with this one, with ours, it's like 53%. So small gain, not as much as the Rotterdam data set, but that's fine. Okay. Okay, I want to summarize that, not what I've talked about, maybe a few directions that what we want to do is that, let's say, with weak supervision, but I also want to maybe go to unsupervised, let's say, unsupervised learning or multimodal learning that was, for example, using images and also point cloud to do the multimodal learning or self-supervised learning. And another one that I'm currently interested in called deep generative models. I think I don't have time to talk about that. And that, so with generative models, it's actually a very interesting topic. So then there's a book a few years ago that would do this multimodal thing understanding. And I was sent to my collaborators and the students here. So I want to stop here, and thank you.
Thank you very much.
It's a very impressive presentation, I would say.
Maybe taking too long.
Very good.
Okay, very good results indeed, and a lot of experiments with networks. So, you know, we are not that much involved in machine learning. Probably Mitko is our expert in machine learning. Mitko, would you like to jump and ask a few questions, although we are a little bit late?
Yeah, I cannot say that I'm an expert. I've worked on 1 to 2 projects using machine learning, and I know a bit those networks that Michael mentioned. It is really impressive what you have done so far. It is really amazing. So many networks, so many projects, exactly targeting images and point clouds. What we did last year was we use point clouds, and I have more experience in point clouds and not images. Although usually the results are a bit better with images, but what we did last year was classification of people, kind of predicting the speed and direction of movement of people in point clouds. And what I wanted to ask you exactly one question about this project. What we did, we didn't finish it till the end because due to lack of funds. But what I was very interested in this in that project was semantic labeling using synthetic data. Because I didn't see that you mentioned anything about synthetic data, and I was very interested in this topic. If we can use synthetic data, I managed to generate a kind of a simulator for point clouds where I simulated at the same time.
Unity.
Yeah, in Unity. Pedestrian movements and their body shape, different characteristics, and so on. It was an interesting project.
Because this project was during the COVID, probably, Mitko, I have to explain.
Yeah.
Sorry that I'm interrupting you. And we didn't have any movement of people on the campus, so we couldn't collect any data. So Mitko simulated the scanner and the race of the scanner and run agents within the view, and yeah, actually all the point clouds that were collected were simulated point clouds.
I analyzed the Kitty dataset before that, because in the Kitty dataset you have images and point clouds labeled. When you see the point clouds, they are very the labeling points are, I mean, done. The process is done like with very bad precision, I would say. They used mainly those 3D boxes that you mentioned, and when you see the accuracy is not that great, but with the synthetic data, the accuracy is like 100%, more or less. You need to introduce some like randomness in the simulation process for the scanner and so on, but this is achievable And there are some papers exactly telling you what to simulate, which errors, and so on. But at the end, what you get is perfectly labeled points. And this is something that I really wanted to kind of explore and go further. Unfortunately, we couldn't finish it till the end, but the results that we were getting were very promising. We could label more pedestrians accurately, and the bounding boxes were more accurately defined, and like we had way better results than with only using the Kitty dataset. Exactly, I wanted to ask you your opinion, and what do you think about synthetic data? And you mentioned that you need to kind of for some things, for some labeling process, to go with only labeling partially the model and so on. But with generative synthetic data, usually you label everything correctly, and it's very quick.
Yeah, it's very good. Yeah, very, very good. I would think that synthetic data, yes, is obviously one way to go. Yeah. So in the past, we've been done a bit on the synthetic data generation before I joined ITC. But then the problem always with synthetic data is that you have this kind of, so once you train on synthetic data, then you kind of mitigate to the real data. You have the kind of domain gap. So you always have to think about this kind of domain gap, or like a domain shift. So there's also a lot of work, let's say training on synthetic data and then evaluating on the real data. So that's actually more for the autonomous driving, yeah. So for that driving scenarios.
I was thinking more to go with transfer learning, where you will kind of pre-train on the synthetic data, and after that go with the real data, or maybe mix them or something like this.
Yeah, definitely. I would think that this kind of one good way to go. Yeah, with
there's several combinations.
Simulations, yeah, with combinations. So I think there's quite some groups also working on that. Well, I didn't have time to show you this, but I don't know if you see that. We actually, so this is our very recent project. So it's just starting last year. So I didn't talk about that. Because we also now can kind of do deep generative models, yeah, with the images, and then we can generate 3D point cloud. So it's quite promising. It's kind of generative models, but then it's not there yet because we also want to generate the so this is the one we can generate at the moment for the real images, but then for the, let's say, real with our interest, yeah, with the buildings, it doesn't work that way. So we've tested it looks very bad, and so there's a long gap to go. So that's what we can do at the moment. Yeah, so this is what we can do at the moment. So I think this kind of deep generative models is also another way, let's say, compared to the let's say simulation. Obviously, there's a lot of people working on the simulation part, then use transfer learning, as you said, and then we make an. But I don't know how much the gap it is, right? Depending on the application, because the real data you have a different sensor noise, and so usually with simulation, then you really get perfect data. Or you would also, let's say, simulate the noise of the sensor noise.
Sometimes you can even simulate better some things because you cannot exactly collect what maybe you want. For example, with what I was doing, I was simulating different body shapes of pedestrians, and I could simulate like I could scale different body shapes like in different directions and so on. You can attach like that they are wearing something, and usually you can collect a bit more diverse data compared sometimes. I mean, it depends what you want to do and on the application, of course. But sometimes if you want specific data set or something like this, you might be able to generate it through simulation easier than by trying to collect it or something like this. And for example, in autonomous cars, you maybe cannot have specific scenario happening in reality, but it's possible, you know. And that's why if it depends what kind of data you are trying to collect. Either it's static or dynamic. If it is dynamic, maybe it is better to simulate it, because maybe you can simulate specific scenario that is possible to happen. Well, you cannot record it easily.
Yeah, I totally agree.
Yeah.
I think for some scenarios, example, let's say for the traffic safety, yeah, for some accidents, and it's very rare. And then if now, like what we develop or other develop these deep learning models, and then you really need a lot of training data for that. And that's very difficult actually to get in such kind of rare instance. Yeah, so the simulation is, yeah, definitely one way to go.
Yeah, I think it's interesting, and yeah, if you have such kind of project, yeah, we can work together. Yeah, because we have some experience about simulating data, pedestrians, and especially for point clouds. For images, I think it's more difficult to generate more realistic or something that is similar to real data. But for point clouds, I think it's easier to match the real data through simulation.
Yeah, yeah, that would be interesting, because we have a recent project from EU working on the traffic safety, so using AI methods with point cloud and then image data to basically you have the vehicles and then pedestrians and cyclists. In Netherlands, it's actually very common. So some areas they are shared, it's called shared space. So in the shared space, then it's actually a bit dangerous, and just they don't know that which one goes first. So we want to investigate that. So we have a new project coming, so working on that. But then they might missing this data issue. Yeah. So we're thinking that we may also want to hire students working on this simulation part for this real event.
Yeah, it sounds interesting. Thank you, Michael. That was really amazing. I will leave now the floor to other people to ask questions.
Yeah, I don't have that much questions. It's quite interesting and amazing. Probably what I was wondering, you show a very good results with the training and on a specific areas within the city. For example, you show the Rotterdam data set. Did you try after that to classify different parts of the city using the same network, and what is the result? Do you need to do some other kind of training to do again training?
Yeah, that's good. Very good. I think I got your question. So basically, let's say you train this area, and then so actually we test on different areas. So for the Rotterdam, there's no problem. So can really test very high accuracy. So with different areas, so basically
different city, for example, can you?
Yeah, different cities, there's no big problem. Yeah, but Netherlands is very similar. Well, we did in the other projects that we actually trained on the French data set. And then we test here, it doesn't work much. So it's the performance drop half. Yeah, so you really see the difference. So I think for Netherlands, it's quite so relatively easier because they are very similar in many areas, like Rotterdam, Amsterdam. But then if you apply that to German cities, that's
identifiable.
Different. Yeah.
It's going to be interesting if you give you some data from Sydney. Actually, Sydney is quite, almost every house is different.
Yeah, I can imagine. So
and also the vegetation is quite different, much bigger, goes above the houses and the buildings. Yeah.
So even for point cloud, that's a bit less problematic, but for images, it's a real problem. If for different seasons, you have different vegetation of the leaves, and with other leaves, and then there's the accuracy basically drops.
Mhm,
Yeah, so I think there's a long way to go if you really want to adapt that to different cities or different countries. So it's not that robust. Let's put this way.
And what would you suggest that actually, if you get a new area, first you have to anyhow train, and after that classify, or
maybe not train from scratch, but maybe a bit fine tuning would be needed.
Okay.
Yeah, so yeah, then it's a different scale. Yeah, so maybe train that some kind of work takes in a few days, but then fine tuning taking a few hours.
Okay. Yeah. Okay. Yeah. Okay. So thank you very much. It was really very interesting. And yeah, if somebody else wants to ask something. Actually, some of our colleagues from civil engineering were not able to join. They have lectures exactly in this period. So they'll watch only the video and might contact you later.
Yeah, you're welcome.
Some questions.
Someone wants the slides, you can just contact me. I can also share the slides. Yeah, no problem.
Okay.
Yeah, I was nice. Yeah, talking to some colleagues.
Yeah, thank you very much. Jack, back to you.
Okay, yeah, thank you very much. Once again, that was a really fantastic presentation and all set for lots of exciting development in the next few years of the research. Very exciting work. Thank you once again, Dr. Yang. So, okay, we'll conclude it there, and we've got just another 2 Pointcloud workshops at the last Thursday of each month for the rest of the year. So we'll look forward to seeing everyone at the next one. Thank you, Michael.
Yeah, thank you. Thank you for inviting me. Yeah,
have a good
my
day.
pleasure.
Have a good day.
We're just starting the day.
Yeah.
Yeah. Okay. Yeah. Bye.
Bye-bye.
Bye.
Bye-bye.
Bye.
Bye. Thank you.
Bye.